Now, our lecture section did not have lecture on Thursday. That is the lecture that, in principle, would have covered section 1.1 of the course, of the book. And we're also going to miss a lecture on Thanksgiving Monday. So we're going to have 2 fewer lecture sections than any of the other than almost all of the other sections. As a result of missing section 1.1, I'm going to talk about that section quite quickly. That's the section which, in some sense, reviews vectors and vector notation. Now, you would not have gotten into engineering if you hadn't seen vectors somewhere, I think. For many of you, vectors are arrows that have length and direction and a column of numbers. And that is what vectors are, in some sense. We're just going to try and, I'm not going to talk about them at length. The book does a nice job. I'm just going to review some things that are going to be key for today's lecture. So first of all, at some point, you learned about Cartesian coordinates. And so Cartesian coordinates are for the plane. You have an infinite plane. You have perpendicular axes. You put equal spaced tick marks along the axes. They might be an inch apart, a mile apart, a light year apart, but they're equally spaced. In high school, you would have called this the x-axis and the y-axis. In linear algebra, we're going to call this the x1 axis and the x2 axis because we're going to be getting out of 3 dimensions quite quickly. If you're in 2 dimensions, you can talk about x and y. If you're in 3 dimensions, you can talk about x, y, and z. But if you're in 25 dimensions or 30 dimensions, you're going to run out of alphabet letters, and also it just gets confusing. So we're going to talk about x1 and x2 instead of x and y. And you remember from some point in your life that every point in the plane can be given a Cartesian coordinate. So this point P would have Cartesian coordinate P1, P2. What that means is that if you go down, this is the distance P1. And if you go across, this is the distance P2. If you're in the first quadrant, P1 and P2 are both, the coordinates are both positive. Here, the first coordinate would be negative, the second coordinate would be positive, but it would still have to do with distances. So these are this is the Cartesian coordinate for this point. Then you have the position vector. So P, which is P1, P2, is the position vector. For the point with the Cartesian coordinates P1, P2. And for example, and then we talk about, so here the language that may or may not be new to you would be position vector. It means the vector that starts at the origin and ends at the point. That might be new. So let me just reintroduce you to planes. So first of all, x, which is the span of 2 vectors, u1, u2, with u1, u2 in R3, not collinear, or 0, is a plane through the origin. So what I'm saying is that if you look at every linear combination, of u1 and u2, as long as they're not collinear or either of them is 0, you will get a plane. So we've been through this. You have two vectors. And once you talk about every linear combination, you're going to get everything in that quadrant, everything in that quadrant, and so on and so forth. So you believe on some level that this is a plane through the origin. It's through the origin because t1 equals t2 equals 0 gives you the 0 vector. And so one thing that you need to get your head around is this is a collection of vectors. When I start talking about its being a plane, I'm considering those vectors to be the position vectors. So if I have a particular vector, that's the vector p. This is the Euclidean, that's the component p1, p2. So you can think of the vectors as being the position vectors, the points at their tips. Each of those points, they lie in a plane. If I want a plane through a point, so x equals p plus t1 u1 plus t2 u2 is a plane through the point given by p1, p2. So this is the vector representation of a plane. Now, the version of a plane that you're used to from high school was ax1 plus bx2 plus cx3 equals d. Or maybe you wrote it as ax plus by plus cz equals d. This is the scalar equation for a plane. So here, this is the one that you saw in high school. And we just want to reconcile, we want to understand how to find the scalar equation for a plane. So I'm going to try and draw a plane in 3 space. So here's some plane. And here is a point. That's a vector in the plane. That's the position vector for a point in the plane. And here's the position vector for another point in the plane. So the head of this arrow and the head of this arrow are both in the plane. So first of all, we have the fact that the vector, so the vector p, is it actually in the plane? Does the vector p lie in the plane? Well, it does if the plane goes through the origin. But if the plane does not go through the origin, then I'm talking about some plane here, the origin's down here, p is connecting my wrist to the origin. The vector p is not necessarily in the plane. Because whether or not p is in the plane depends on whether the plane goes through the origin, and I didn't tell you. P may not be in the plane. And x may not be. But what about x minus p? So if I subtract these and I get that vector, that's going to be either in the plane or at least parallel to the plane. Either in the plane, that would be if the plane goes through the origin, or is parallel to the plane. So this tells me that one way of getting a scalar equation for a plane would be if I just said, I want these things all x so that x minus p is parallel to the plane. You can either talk about parallel to the plane, or you can talk about orthogonal to something that's perpendicular to the plane. So this is the big idea. So I have my plane, which might not be going through the origin, but for sure, it's got a normal vector. N is the normal vector to the plane. So plane N is perpendicular to every vector lying in the plane. So N dot x minus p must equal what? 0 for every x in the plane. Every x which is position vector for a point in the plane. So let's do an example. So I'm telling you, so example, determine the scalar equation of the plane that passes through the given point with the given normal vector. So I'm asked for the plane that passes through the point P6 minus 2, 5, and with the normal vector N is equal to 4 minus 2, 1. So first of all, I need to translate this from a point in the plane to a position vector. So the position vector for that point is 6 minus 2, 5. And so the scalar equation is the dot product between the normal vector, 4 minus 2, 1, dot producted with x1, x2, x3, minus 6 minus 2, 5, equals 0. The reason this is the scalar equation is when you take a dot product between two vectors, you get some number. Yes?
I thought the coefficients of the scalar equation were the normal.
Well, that's exactly what we're just doing.
Oh, but I thought the normal vector was 4, negative 2, 1, so wouldn't that just be the coefficients?
Well, that's what we're going to find out.
Oh, okay.
So this translates to 4 minus 2, 1, dot product x1, x2, x3 equals 4 minus 2, 1, dot product 6 minus 2, 5. And then that translates to exactly what was just pointed out, except this time you see why it's true rather than just having been told to memorize it because you're in high school. 4x1. To be fair, probably your high school teacher derived it for you. I shouldn't be mean to your high school teacher. Equals 24 plus 4 plus 5 is 30. 24, 30, 33, no? 24 plus 4 is 28 plus 5 is 33. So the only thing that's nice here is that you get to see where that 33 came from. And so using these vector equations, you can do all sorts of problems like find the equation for the plane that's given through a point and is parallel to a plane and blah, blah, blah. But that's that. So tomorrow is cross products. Are there questions?